To explore different supervised learning algorithms, we're going to use a combination of small synthetic or artificial data sets as examples, together with some larger real-world data sets. Scikit-learn has a variety of methods in the sklearn datasets library to create synthetic datasets. The synthetic dataset we'll use for illustration purposes are typically low-dimensional examples, because they only use a small number of features, typically 1 or 2. This makes them easy to explain and visualize. Many real-world datasets, on the other hand, have a higher dimensional feature space. In other words, they have dozens, hundreds, or even thousands or millions of features. So some of the intuition we gain from looking at low-dimensional examples doesn't always translate to high-dimensional datasets, and we'll discuss that a bit more later. For example, high-dimensional datasets in some sense have most of their data in corners with lots of empty space, and that's kind of difficult to visualize. We'll go through some examples later in the course. But the low-dimensional examples are still useful so that we can understand things like how a model's complexity changes with changes in some key parameters. So for basic regression, we'll start with a simple problem that has one informative input variable, one noisy linear output, and 100 data samples. Here's a plot of a data set using a scatter plot with each point represented by one dot. The x-axis shows the feature value, and the y-axis shows the regression target. To create this, we use the makeRegression function in sklearn datasets. Here's the code in the notebook. To illustrate binary classification, we'll include a simple two-class dataset with 2 informative features. Here's a scatter plot showing each data instance as a dot with the first feature value corresponding to the x-axis and the second feature value corresponding to the y-axis. The color of a point shows which class that data instance is labeled. I'm calling this dataset simple because it has only 2 features, both of which are informative. In this case, these 2 classes are approximately linearly separable, which means that a basic linear classifier placed between them does a pretty good job at discriminating the points in the 2 classes. So turning to the notebook, to create this dataset, we used the makeClassification function in sklearn datasets, creating 100 points that roughly group the data samples into one cluster per class, with here a 10% chance of randomly flipping the correct label of any point, just to make it a little more challenging for the classifier. We'll also look at a more complex binary classification problem that uses 2 features, but where the 2 classes are not really linearly separable, instead forming into various clusters in different parts of the feature space. This dataset was created in 2 steps. First, using the makeBlobs function in sklearn datasets to randomly generate 100 samples in 8 different clusters, and then by changing the cluster label assigned by makeBlobs, which is a number from 1 to 8, to a binary label by converting it using a Module-2 function, assigning the even index points to class 0 and odd index points to class 1. To illustrate multi-class classification, we'll use our familiar fruits dataset, which, as you may remember, has 4 features and 4 possible target labels. Here on the left, I'm showing the array of scatter plots that we saw in week 1 that shows the relationship between all possible pairs of features and the class labels, with the distribution of values for each feature along the diagonal. To illustrate a real-world regression problem, we'll use a dataset derived from the Communities and Crime dataset in the UCI repository. Our dataset uses a subset of the original features and target values, which were originally created from combining several U.S. government data sources, like the U.S. Census. Each data instance corresponds to a particular geographic area, typically a town or region of a city. Our version of this dataset has 88 features that encode various demographic and socioeconomic properties of each location, with 1,994 location data instances. The target value that we'll try to predict is the per capita violent crime rate. To use this dataset, we use the load crime dataset function that's included with the shared utilities module for this course.